Alright, so this lecture will resume discussing things at the network layer. So we discussed IP addressing last lecture, and we realized that the forwarding tables at a router could be complicated, and how those complications play out in the actual forwarding decision we'll see in today's lecture. Before we start that, I just wanted to mention this protocol, which also runs at the network layer, which is ICMP. This is the Internet Control Message Protocol, and this message protocol is used to exchange control information on the network, and it's used both by hosts as well as routers. So it runs in the network layer, and it can be used either in the end network or inside the core of the network. So when you use a program called ping is really sending out these packets, which are ICMP packets. Another interesting application of ICMP is a program called traceroute. So you have seen traceroute being discussed earlier in the class. We have seen examples of what a traceroute output looks like. Does anyone know how traceroute works? So what does traceroute do? Traceroute lets you trace all the routers in the path between A to B, and it does that by using sort of a clever hack of exploiting features of ICMP. So if you look at ICMP, a typical ICMP message will have a type plus a code. Now look at type 11 of the ICMP packet. This is a packet which a router will send back if the TTL of your original packet is expired. So remember, each IP packet has a TTL field, time to live field, and every router is going to decrement this field. So if you have routers in your path and you send out a packet with TTL equals 3, when it crosses the first router in the path, TTL becomes 2, then TTL becomes, and finally here TTL equals 0. When TTL becomes 0, this router not only drops this packet, but it will also send back an ICMP packet to the source with the code 11 that TTL has expired. Now what traceroute does is it starts sending out sequence of packets with increasing TTL starting from 1. So it will send out a TTL with 1. That packet has to be dropped by the first router. So you will get an ICMP reply back from the first router, and from this packet that you receive, you can identify which is the first router in your path. Then you send a packet with the TTL field 2. It will successfully cross this router, but then it will have to be dropped here. So you get an ICMP reply from this router, and so on and so forth until you probe all the routers in your path. Now sometimes when you run traceroute, you won't get a reply from certain routers, and those routers do not send back ICMP replies, because this could also be used to launch some sort of a denial of service attack. It requires a lot of processing. But for routers that honor this ICMP packet, you can use, traceroute uses ICMP to trace the route. So this is a way an end system can probe into the middle of the network. Okay, now let's start discussing what happens inside a router. So we got some idea of how a router forwards a datagram on the internet. So in the discussion that we have today, in today's lecture, we'll be assuming that this router is running on the internet. So it's forwarding packets based on IP addresses. So we'll get to understand the principles. The principles are the same if you're running forwarding on a virtual circuit network or other kinds of networks, not datagram networks, but all our examples will be with datagram networks. So recall from the last lecture that routing tables look something like this. The network, the destination network is identified by a prefix. Given a prefix, you identify the next hop router and the port on which, or the link on which the next hop router is connected to. So if you get a packet at the input link of this router, it look at the destination address, decide which is the network this packet is destined to, and from this table it will choose the appropriate port and put the packet there. So conceptually this sounds very simple. So the prefix will uniquely identify which physical network this packet is going to from the network ID. Now remember, from the CEDAR addressing scheme, this network ID could have a variable number of bits. So your forwarding decision has to depend on this identifying the network ID which does not have a fixed number of bits. So the first very simple forwarding decision is this datagram for a host on your local network? If it is on the local network, then you don't need to go to this table, make this decision and forward it to the next hop router. If it's not on the local network, then you consult the forwarding table. What does a high performance router looks like? Well, the high performance routers which have capacities of 160 gigabits per second or 80 gigabits per second, they are massive machines. So the Cisco GSR 12416, for instance, is 6 feet high. It consumes a power of 4.2 kilowatts an hour. So this is as tall as a human being, and the power that it consumes is 4 times that what a human being consumes. So what a lot of the future problems people expect with these routers is the amount of power consumption. The amount of power that's consumed and the amount of heat that these routers generate. And if you place all of these routers together, let's say at a network access point or a large ISP, then just the amount of money you have to spend on air conditioning can be prohibitive. So the amount of power that is needed is really high, and we'll see where this power is used. So these are what modern routers look like, and inside the router you have basically 3 different parts. One is the input switch or the input link where all the packets are coming into a router. So that is the input port of a router, and you have multiple input ports depending on the number of input links that you have. The second part of a router is the interconnect. The interconnect is what will connect the input port to a particular output port. And so the third part is obviously the output port, where these packets are finally put on the appropriate link and forwarded along to the next hop router. Now we'll look at details of every piece of what's inside a router. So if you look at the input ports of a router, you'll see that every port has its own copy of the forwarding table. So the forwarding table is common, but it's replicated at each input port, because you don't want every input port to go to some central location, get the forwarding table information, and then make the forwarding decision. Because making this forwarding decision is computationally very expensive. So you want to parallelize it as much as possible. So every input port will have its own forwarding table. It's not sitting in some centralized location, and every forwarding decision is made independently of the other. There's no centralized processor except in software routers which is making this forwarding decision. Okay? So forwarding in an IP router, you look up the packet destination address in forwarding table. You see if you have a match for the network. If it's known, you're going to forward it to the correct port. If it's unknown, you'll drop the packet, and you'll also generate an ICMP message that this destination is unknown or unreachable. That's what a router is going to do. If it's known, then the router decrements the TTL. So that's also part of the processing of the router. So not only does it have to forward, it also has to process the header. So it decrements the TTL, and once the TTL is decremented, you have to update the header checksum. The bits are changing. And then after the processing is done at the input port, then it's forwarded along to the appropriate outgoing interface. So how is the address looked up in a real router? Well, originally the address was looked up based on class-based addressing. Given a destination address, you could figure out which class this destination address belonged to, class A, class B, or class C. Once you knew that, then you had an exact match based on the class, the number of bits that you had to match. You go to the routing table, look at the exact match, and pick out the port number, and then you can forward the packet along. So if you're doing exact match, there are many ways to do an exact match in a table. But if you're doing CEDAR, then things become a little bit more complicated. If you're doing CEDAR, then you don't have that class-based addressing. Rather, you have these prefix-based nodes. And here, exact match will have certain problems. So the first thing to note is that the search operation of searching for the entry corresponding to a destination address is not a direct lookup in a table. Why is it not a direct lookup in a table? Yeah. Well, longest match also you can do a direct lookup, right? Yeah. Direct match would be too big. If you have 32-bit IP addresses, then a direct match requires 4 gigs of entries. You cannot possibly fit that in the memory of a high-speed router. So direct match is going to be too big. First of all, you don't need 4G entries, right? Because you're going to forward it to networks, prefix based. The number of networks is going to be much smaller than 4G. So you want something which is better than a direct lookup, which is faster than a direct lookup. So what you have are associative lookups, and associative lookups come with these hardware devices called CAMs, or content addressable memories. So what CAMs do is, given a search data, it can associatively look up the memory address based on the search data, and it gives you a hit on the port number. So based on the content, you can get an address on this CAM in order 1 time. So the advantage of using CAMs for this lookup is it's very simple. You need only the number of entries which is equal to the number of networks or the destination prefixes that you have in your routing table. You don't need to fill up the entire lookup. It's the number of operations needed is O of 1. So it's sort of independent of the length of the prefix. But then again, it's very slow. It consumes a lot of power. You can't have large CAMs. So the size of CAMs is restrictive. So if you have a large routing table, a large number of destination prefixes, then you cannot fit all of them into a CAM. Finally, they are very expensive. The search operation is also not an exact match search. An exact match search is you search for a key in a collection of keys of the same length. So why is the search operation not an exact match search? I'm sorry? Yeah, you want a longest match search. So you can have an exact match search for a part of the prefix, but what you're really looking for is a match of a longer prefix. So if you're doing exact match search, then you have some well-studied data structures which use hashing or balanced binary search trees. So suppose you were doing an exact match search using hashing. How do you do it? Well, we had established that we don't need a direct lookup table which uses all 32 bits, right? Because the number of networks that exist is much smaller than 2 raised to 32. So what you do is you build a hash function which maps the network address into 16 bits. The domain of this hash hash function will give you 16 bits. Then you go to an address in a memory where, depending on the hash function, you will have the entry corresponding to the input. So now you have reduced the size of this table from 2 raised to 32 to 2 raised to 16, much smaller, and you can possibly fit that into memory. How there is a problem though. So for lookups using hashing, the hash so you have a hash function which operates on the address, and it gives you some results. Now, if you had a perfect hash function, then you will have no collisions in the result, right? But it's very difficult to construct a perfect hash function. So for many different inputs, your hash function will have a collision. So you'll have a number of different original addresses which will hash to the same key. So here in the memory, the rows are the results of the hash function. In the perfect scenario, each row will have only one entry, assuming that your total number of results is less than 2 raised to 16. So that's the perfect scenario if you have a perfect hash function. But it's difficult to construct a perfect hash function because the distribution of the networks is not very standard. So what you'll have instead is that you'll have every row will have a variable number of entries for the result of the hash function, and those correspond to the hash collisions. So once you get the result from your hash function, then you have to linearly search through these entries to get your result. So suppose your hash function will give you the same result for these two destination addresses. So you go to the same row, let's say row 44 in the memory. Now the output ports for these two destination addresses are different. So what your memory contains is the result for each of the input function, the input variables. So it will have the output port for the first address, the output port for the second address, and all the collisions that you have. So you create a linked list for all the collisions that you have, and you search through that linked list in a linear order, and that will give you the destination, the right destination port. So the advantages is that it's simple and the expected lookup time can be small. So on an average you won't have hash collisions, but the worst case performance can be bad, and this results in a non-deterministic lookup time. So you cannot guarantee that the lookup time is going to be some value, because a priori you don't know how long this linked list is going to be in a particular row given a hash function. And it's sort of inefficient use of memory. So you can use multiple hash functions to improve on this lookup time, and there are several research papers that look at this problem. Another way to do this exact match search is to use a binary search tree. So if you have n bits in your address, then a binary search tree will do log n comparisons and come up with the answer given a destination address. So binary search trees, which comes from retrieval, looks something like this. You look at the first bit, decide whether it's 0 or 1, and go down this tree, looking at it one bit at a time. And a fully balanced binary search tree will require log n memory references, regardless of the number of addresses. And the number of memory references is crucial. Yeah.
But I'm not clear how hash function will solve the problem of not having exact match first. Not having exact, you don't want to have exact match. In fact, how can a hash function solve the problem? Because it's always an exact match first in a hash function.
So what you do is you have multiple hash functions based on different number of bits. Yeah, and then you choose the one with the longest matching. So it becomes very complicated. Yeah. So that's why hash searching is good if you want an exact match search. So that was this is a binary search tree. You can have multi-way trees. A multi-way tree is going to reduce the number of memory references. So instead of having a binary decision, you can have a multi-way decision. So what you can do is you can look at, let's say, 4 bits at a time and go down this tree 4 bits at a time. So now the number of memory accesses is going to reduce. Right? The depth of this tree has reduced now. So the result of your match is going to give you the prefix and a pointer value. If the pointer value is 0, that means that this node has no children. So it stops here. There isn't going to be a match below this node. If the pointer value is not 0, then you go down to the tree and search. So this will reduce the number of accesses. So you have a 16 array search tree here where you're taking 4 bits a time. Why can't we have a 32 array search tree? Not 32 array, but 2 raised to 32 array search tree. No, it doesn't really become the hash function.
Or it becomes the worst case management.
So what are the memory requirements of a 2-way search tree versus a 16 array search tree? What starts happening as you increase the number of bits or the degree of the tree is that a lot of these nodes will have this pointer value 0. They're not going to have any children. So you'll have a lot of entries in your data structure which are really useless. They're not going to have any children. So as you start increasing the degree of the tree, what starts happening is that the memory requirements go up as the number of bits that you're checking on goes up, but that memory is very inefficiently used. Most of the entries there have this pointer value 0, they have no children, and so if you were doing, let's say, a 256 array search tree, and you're looking at an address space which was filled, let's say, 10%, then almost 99% of your data structure is going to be wasted. If your networks are randomly distributed over 32 bits, and the total number of networks is 10% of the size of the total available size, then as you start increasing this multi-way, the degree of the tree, then you start wasting more and more space. So you need a larger memory in the router to implement this. Memory is expensive, but that memory is going to be wasted. So that's why there's a trade-off in choosing the degree of the tree. You reduce the number of memory accesses that are needed to get a search, to get a match, but you give up a lot of wasted memory. So we realized earlier that what we really need to do in CEDAR style addressing is to get the most specific route or the longest matching prefix for a given address. Because these line segments can overlap, you have to look at the prefix length which is the longest. So the longest matching prefix really corresponds to going to the line segment on top of this structure. That corresponds to your particular address. If you do a match based just on 16 bits, then this match is going to give you the incorrect route. You have to look at the match which is based on 21 bits. So you'll have two different matches, but you have to go with the match which has the higher number of bits with CEDAR. So one way it's done is by using what are called ternary cams. The ternary cams, again, it's an associative memory, but the memory is arranged in the order of the longest matching prefix, or the most specific routes appear closest on top of the table, and you do your matching in parallel. All the results that are matched will produce a 1 in the output, and then you have a priority encoder which decides which of the results to use. So given a destination address, you'll have a match, let's say, with 16 bits, and you'll have a different match with 21 bits. This ternary cam will produce a yes or a hit for both of those. But after the ternary cam, there's another hardware element which chooses the right hit. Yeah.
So if you're given a destination IP address, and like you said, you can get 2 hits with different prefix lengths.
Yeah.
I'm kind of confused about how you would know which route you would need to take, which is the correct destination.
So you arrange in this ternary cam the addresses such that the longest matching prefix or the most specific route is on top of the table. So you get results, you will get multiple hits, but what this device does is it will just choose the one which has the smallest address in terms of this memory. So which is on top of the table, that's picked as a most specific route and that's chosen. You can also do longest prefix match using binary trees. Now they are not balanced. So suppose you have these different prefixes. Some are 5 bits long, some are 3 bits long, some are 8 or 10 bits long. Then what you do is you construct this binary tree, and when you get a matching prefix, you terminate that node, and at that node you will have the right entry for that particular prefix. So at every bit you make a choice, you go down this tree, and as soon as you hit a prefix that matches, you have a result. A variation of this binary tree is the Patricia tree. Patricia tree lets you collapse certain nodes. So the node J in the binary tree appeared way down here, so you needed to make decisions here, 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 here. You needed 4 extra decisions which are not really needed given the structure of this prefix table. So you can collapse this tree and have a much more compact data structure which will require a lot fewer memory accesses. So when you reach this point, instead of looking at the next bit, you skip 5 bits and see if the 5th bit after that is 0 or not, and that will give you the most specific or the longest matching prefix. Yeah.
Trees as well.
Multiple,
Like you get multiple networks that match.
Yeah, actually, that's a good question. I was about to explain that you can get multiple matches, and that could cause a performance problem. So let's say you have a prefix table then you have some output ports, port 1, port 2, port 3, port 4. So now, if you have a destination address which has the first 2 bits 1, 0, then that could potentially match P2, P3, P4. Right? It could potentially go on these 3 output ports. Or no, let's just deal with let's make okay, this is better. Yeah. So if your first two bits are 1 and 0, then you can have 3 different matches. If your first 4 bits are 1 0 1 0, then you can have 2 different matches. So if you're building a Patricia tree here, by skipping certain bits, so you can skip the first bit. The first bit is never going to be 0 here. So you just check bit 2. And if this bit is 1, then you have the answer that P1 is going to be used. If it's 0, so you check bit 3. If it's 0, you have P2. After that, if it's 1, if it's 1, bit 3, what is the next bit that has to be checked? Bit 4 is 0 for both of them. So you don't need to check bit 4. So you need to check bit 5. So you check bit 5. If it's 1, you have port 4. If it's 0, you have port 3. Now, let's say you want to route a packet which has the destination address has the first 5 bits. How are you going to use the Patricia tree to choose the right port? Well, the Patricia tree tells you that you have to first check bit 2. You check bit 2 and it's 0, you go down here. The third bit is 1, right? So now you go here. Now what you're going to do, now the problem is you have not checked bit number 4. Patricia tree is telling you you just have to check bit 5. So you check bit 5, you go here. And what you discover here is that your prefix is of the form 10101. So this is not the right match when you arrive here. Right? So what you have to do is you have to go back. And you go and check here. This is also clearly not the right one because this bit has to be 1. So now you go 1 level up. And then go and check here. And then you see that this 1 0 part is matched by P2. So Patricia tree will let you compress the search tree. On an average, it will give you a lower number of memory accesses, but sometimes you'll have to backtrack, and that backtrack can cause complicated implementations. Do you see the problem here? There's nothing wrong with the way we construct the tree. We compress the data structure, so on an average the number of accesses is going to be small, but depending on the input distribution you might run into problems, and when you run into problems you have to backtrack. So this does not give you a conclusive answer going down this depth of this tree. If you get into an error scenario, you have to backtrack. So now let's look at the lookup performance required in the router given different kinds of line rates. So line rates is the rate at which the router is processing packets. So if you have a T1 line, it's the bandwidth is 1.5 megabits per second. Now depending on the packet size, the portion of that bandwidth that belongs to the header is going to be different. So the smaller the packet size, the more headers you have to process for the same equivalent bandwidth. So for an OC192 link, which is 10 gigabits per second, if you have packet sizes which are 40 bytes, they are ACK packets, then the worst case number of packets that you have to process per second becomes 31.25 million packets per second. If you have larger packet sizes, then you have to process a smaller number of packets per second, but 5 million packets per second is still a lot of processing. So you get a packet, you have to in 1 second do it 5 million times. So your per packet processing budget is 1 over 5 million in terms of seconds. And in that time budget, you have to make all the different memory accesses, search through these different data structures, come up with the right forwarding table result, and send the packet across. So that's why it's very important to optimize the number of memory accesses. If you look at modern routers, the limiting factor behind their speed is in the speed of the memory, the number of memory accesses you can make, and that comes from these complicated data structures that you have to deal with in trying to get the right result. So the limiting factor is not the speed at which you can put the packet onto a link, your modulation scheme, or the signal to noise ratio in the element that you're using, the copper wire or fiber optics. The limiting speed is the number of memory accesses that you have to make and the speed of the memory that's used in a router. Yeah.
On average, like how much time it takes to access one?
Again, it depends on different kinds of memories, whether it's a CAM, TCAM, DRAM, SRAM. Different memories have different speeds of accesses. TCAM is the slowest one of them all. Yeah, SRAM I think is the fastest.
Okay.
I can give you the numbers. I think the fastest access is 40 nanoseconds for one access. Now once you have made this forwarding decision, once you know which port this particular packet has to go to, which output port, the next step is then actually sending that packet to the right output port. In modern routers, there are two basic ways of doing this forwarding. One is a crossbar, a switching fabric, where you have an interconnect of this form. I'll explain how this works. And this involves input queuing. The other is you use a fast bus as your switching fabric. And in this scenario, what you have is output queuing. So let me explain what the two interconnect techniques are. There's also another interconnect technique which was used in the older routers, or which is used in software routers. And in that scenario, your switching fabric is memory. So you have a shared memory between the input ports and the output ports. The input port will write out the packet and the destination port to this memory, and the central processor will then take that packet, look at the output port, and copy it from the memory to the appropriate port. But that architecture is not used in modern routers or fast routers. They use either an interconnect non-blocking switch fabric or a fast bus. So if you have an interconnect with a crossbar, what that really does is, let's say you have n input ports, so data is coming in at n different input ports, and you have n possible output ports. Then what your fast interconnect will have, it will have n rows and n columns. The rows correspond to all the input ports, the columns correspond to the possible output port. So anytime you want to send a data from a particular input port to a particular output port, then you go along the row to the corresponding output port, and if it's free, then you're given access to this output port, and your data can travel along this way. The packet can travel along this way. If it's not free, if some other input port is accessing that output port, then your data has to be queued up at the input port. When it becomes free, when only your signal in a particular column is active, then you can send that packet across and it goes through in this interconnect. With a fast bus architecture, you don't have an interconnect like this. You have one common bus for all the input ports, but the bus is so fast that all of them can write to it. The memory bandwidth that is needed at all of these input ports is 2 times the processing capacity of the router. Why is that? So you can transmit this packet from the input port to the desired output port when your crossbar becomes free. So to make that operation, you have to first read contents from this memory and then write it out to the right crossbar. So you have to operate at twice the processing capacity. You have to do two memory operations to process one packet. Read it out from the queue and write it out on the crossbar. The other scenario is where you have a very fast bus. And all of the input ports write to this common bus, and then the common bus will write out to the appropriate output port. So if your processing capacity of the router is, let's say, R gigabits per second, what should be the bus bandwidth? In this scenario, there is no input queues. All the queuing that is done at the output port. Think of the worst case scenario where all the input ports want to forward the data to one particular output port. So now think of the total capacity, which is R over N coming in, and the total capacity of the output ports. So in the worst case scenario, this bus has to process all the data coming in from these input ports. So it has to operate at the capacity of the combined capacity of this router. I'll probably give a homework problem which makes you think of this scenario a little bit more. Now, one problem with this input queuing is what's called head of the line blocking. So remember what happens in an input queued crossbar structure where you have this crossbar until the column that you desire becomes available, and that availability is decided by some sort of arbiter or scheduler here. Until that becomes available, your packet is going to remain queued at the input port, right? When it becomes available, you can send your packet across, and then it goes to the right output port. Now, what we had earlier seen was that if you have a queuing system and you plot the queuing delay as a function of the load on that particular link. Then as the load approaches 100%, this queuing delay starts to blow up. So what that roughly told us was that you can operate this input link at close to 100% capacity, or let's say 80 or 90% capacity, and still not incur a significant queuing delay. So if your input link is 10 megabits per second, you can pump in data here at the rate of 7, 8 megabits per second, and still the average queue that you'll see is not going to be very high. And that also means that you don't have to drop too many packets if you're operating at that average link capacity. Now, because of head of the line blocking, this curve shifts dramatically. Now, this blow up starts happening at roughly 60% of the capacity of the link. So if you have a link which is input link which is 10 megabits per second, then as you approach half the capacity, your queuing delay will start to blow up. Now what is this problem of head of the line blocking? Because this causes a severe inefficiency in the way these networks can operate. Instead of operating at near full capacity, you're forced to operate at about half the capacity. So suppose you have a scenario like this. You have three different input ports. The color of the packet indicates which output port these packets are going to. So you have three different output ports: red, green and black. The first packet on each of these input ports is red. So your arbitration scheme will then decide which of these input ports gets access to the first time slot in which the red packet will be transmitted. All three want to go to the first output port. So the arbitration scheme somehow decides that the second input port gets access to the red output port. Now while that is happening, the black and the green output ports are sitting idle. If you look at the network, there are both green packets and black packets which are sitting there idle, which could have used so if it's green, black and red, the black and the green crossbars are sitting idle while the red one is being fought over by the three different output ports. So the head of the line, which is the red packet, has caused blocking for packets which are behind in the line that could have used one particular output port, which are sitting idle. And in the limit, this head of the line blocking causes a drop in efficiency. So in this first time slot, both of these output ports could have been utilized. But because of this head of the line blocking, these packets unnecessarily have to face this delay. So that causes the queue to build up. So this is the head of the line blocking. And it's solved by using virtual output queues. So what are virtual output queues? At each input queue, you arrange those packets in virtual output queues depending on the destination. So now each of the input line cards will have n different queues depending on where the packet is going. So once the forwarding decision is made, then you send that packet into a local virtual queue. And then this arbitration decision is done based on these virtual output queues. And now you have a lot more flexibility and you can schedule all 3 packets in the first time slot. So the red and green packet that was waiting need not wait. And by doing this, you can shift the curve back to nearly 100% utilization. So by implementing this simple scheme of virtual output queues, you can get rid of the problem of input queuing. So we'll stop here. Next lecture we'll look at IPv6. We'll look at issues related to NATs and tunneling.